All right, so parametrics are where you have an x function and a y function, but both defined with a parameter. Usually that parameter is t for time, but they can define it as whatever they want. So both are outputs dependent on an input of t. Okay, so what we've been doing so far up to now is just one directional movement, just a particle is moving along the x-axis, or a particle is moving just along the y-axis. But in parametrics, a particle can move along this whole plane with respect to a certain time. If you want to see the movement of the particle, you're going to want to do a table of values. T, x, y. And then we'll have to plug in values for t. There's no restrictions on t for this equation, so let's just pick nice values of t. We know t can't get any less than what number? We know t can't get any less than 1 because if I put any number less than 1 into that square root, it's going to give me a negative or an imaginary x value. So if t is 1, x is, and y is 3. So we are at 0, 3 at time t equals 1. At t equals, give me another good number. 2 is good. Let's just keep going in order. 2, x is, y is 4. So then we are at time t equals 2, we're at 1, 4. So this particle is now moved there. And then at t equals, give me another number, 5. At t equals 5, x is, and y is 7. So we're at 2, 1, 2, 3, 4, 5, 6, 7. And then I think after that we go off the graph. But t can continue, right? And x's and y's can continue. So it won't get any less than that point right here, this point right here. And then we go in this direction up. And the particle's actually going to keep going, so we'll put an arrow at the end. And then for parametrics, you kind of want to define the motion that the particle goes in. So we just draw little arrows along the way saying, hey, it's moving this way. So you just need a few arrows to tell you which way it's going towards. Okay? All right, to eliminate the parameter, you just want to solve one of these for t and then plug it into the other one. I'll solve this x1 for t. So x squared plus 1 equals t. I just solved for t. And then I take this t and I plug it into the other function. So y equals x squared plus 3, which looks like the graph of this parametric right here. But there are restrictions on this graph, so we want to say x can only be, x has to be greater than or equal to 0, and y has to be greater than or equal to 3. We want to state the restrictions on our parametric function.
How did you get those restrictions?
If you just look at the graph, then this graph only has domain from 0 on, right, on the x-axis. Mm-hmm. And then on the y-axis, it only has range of 3 up, right?
I don't get why that's necessarily a restriction.
Because our t values can't get any. Our graph is only graphed on that domain and range. Because of our t values not being able to be less than 1, right? Like if I can't plug in any other t values to get me the other side of the graph that I would normally have with this quadratic right here. Okay? Yeah.
Could you not just restrict the t, or are you doing
Yeah, if you wanted to, since if you restrict the x is greater than or equal to 0, y is basically already restricted for you. Is that what you're asking?
Yeah.
Yeah, so you can just restrict it with 1. But if with one restriction it doesn't draw just that graph, then you have to restrict
So it's
both.
better just to both.
Yeah. Okay, so try B now. Make a table for me, graph it, graph the parametric, and then eliminate the parameter and restrict your domain if you have to. And the remember it has a domain right here for you, so you can only use values between -2 and 3 for your t. Yeah, that's okay too, as long as you still have that plus or minus in front. Yeah. If you solve for y, that's fine. Just make sure you have the plus or minus in front of the root to get the top and the bottom half of the root. This one you have to restrict both x and y, because if you just restrict maybe if you just restrict the y values, you should be okay, I think. But you can't just restrict the x values, because then people might think that you can go all the way down to -6 here, because it's from -3 to 6, and you don't want them to think that. So make sure you restrict the right thing. And then don't put arrows at the ends of your parametric here, because this has a restricted domain, so it doesn't go on forever, so you don't want to plot more than that little path of the particle. Okay? All right, last one. For this one, we'll probably choose t values that are angles. And the 4 quadrantal angles are probably the best. So 0, pi over 2, pi, 3 pi over 2, and then we go back to 2 pi. And then it keeps repeating itself. So if we plug in 0, what do we get for x? X is 5. 0 in for y is -1. Pi over 2 in for x is 3. Pi over 2 in for this one is 2. Pi in for x, or in for the x function, is 1. Pi in the y is -4. 3 pi over 2.
How's pi in the
Oh, sorry. I skipped one. Thank you. And this is -4. And this is 3. And 2 pi is 5, and -1 again. Right? 1, 2, 3, 4, 5, -1. Okay, this is our starting point right there. And then we go to 3, 2. And then 1, -1. And then 3, 1, 2, 3, 4, -4. And then back to 5, 1. So we're going around like this. Then it just keeps going. That is a ellipse. Right? And it's got vertices of, these two are vertices and these two are co-vertices. You remember ellipses? With our vertices and co-vertices. Okay, how do you suggest we get this function in eliminate t? Arc sine and arc cosine? Oh, yeah, I think we could do that. But then that would be a lot of simplification. Yeah, I like that. So what should we do first with these two? Cosine t equals, what does cosine t equal? X, okay. And sine t equals, okay. So Michael, you said trig identity. Which one do you want to use? Or anybody?
Cosine squared plus sine squared
Equals.
1.
Okay. So cosine squared t plus sine squared t equals 1. And that's cosine t, so it's x minus 3 over 2 squared plus y plus 3, y plus over 3 squared equals 1. And that's the equation of an ellipse, right? You remember this from Algebra 2? No? I don't think we need any restrictions on the domain because it just keeps going round and round, and x and y aren't really limited by anything, so.
If you just know the equation of a ellipse, are you allowed to just use it?
You want to convert first and then just graph the ellipse? You can, yeah. Yeah.
If we did put restrictions on it, we would just be safe, we'd be fine. Yeah, there's no point.
Yeah. Okay, so that's parametrics, and now that we're moving in a two-dimensional plane, a couple things change when we're doing calculus with it. The first one is the first derivative. I still want dy dx, so I still want, for example, like the slope of the tangent line to a point. But now my function is in terms of x and y, or t, and I have two separate functions. That's not really going to be a big issue. I still want concavity, like the second derivative, to tell me concavity at a point. That's d squared y over dx squared. That will change. And then a lot of the acceleration, velocity, acceleration, speed, in distance will change, but we'll talk about all that because we're now moving in two dimensions. So a couple things are going to change when we're doing parametrics. Okay. First one is not going to change. Dy dx is very simple. You just do the derivative of y over the derivative of x, and both with respect to t, and the dt's will cancel, so it shouldn't be that bad. So if they gave you an equation like this, or a parametric like this with an x and a y, then to find dy dx, it's pretty easy. You just take the derivative of y. What's the derivative of 3t squared minus 2t? And then just put it over the derivative of x, which is t to the negative half. Okay, let's maybe make this a little bit nicer. So 6t minus 2 times t to the 1/2, or 6t to the 3/2. Am I doing this right? Minus 2t to the 1/2. Okay, are you okay with that? Yeah? Okay, second derivative, a little bit trickier. So if they ask you to find d squared y over dx squared, they want you to take dy dx, oops, and then they want you to take that and take the derivative with respect to x of dy dx, okay? But where there's a problem, right? Because our dy dx right here is in terms of t, not x, right? So if I take the derivative of this, since it's in terms of t, then I can't just straight take the derivative of this because it's not in terms of, we want it in terms of x. How do I take the derivative of something in terms of a different variable? What? Implicit differentiation, right? Okay, so good. So we'll just take the derivative of this, but this will be, what is this? 6 times 9? 9t to the 1/2. And then this will be times dt dx because we want the derivative in terms of x, not in terms of t. And then minus, this would become t to the negative 1/2 dt dx, right? Some people, since it's in terms of t, just like taking the derivative and then multiplying it by dt dx because you can factor out the dt dx. So if you can remember to do that, then you can do that way. And then, if you've already done your first derivative, you already know that this is what? T to the negative 1/2 is equal to dx dt. So if I want dt dx, I just flip it. So it's 1 over t to the negative 1/2 or t to the positive 1/2. So this will just equal 9t to the 1/2 minus t to the negative 1/2 all times t to the 1/2. And if you want to leave it, you can leave it there, or if you want to simplify it, you can get 9t minus 1, right? So that's your second derivative. They will ask you specifically for d squared y over dx squared. Don't do it unless they ask you for that specifically. That will only give you concavity of the parametric. It's not going to give you, this is not acceleration. Okay, so if it asks you for acceleration, don't use d squared y over dx squared. Okay, so you should be able to try example 2 and 3 on your own. These are the two parametrics. I just want a tangent line. So what do I need for a tangent line? I need 3 things. I need dy dx, I need x, right? And I need y. Those 3 things, and then I can make a tangent line. Okay, so I'm gonna let you try 2 and 3, and I'll put them up here, and then we will figure it out. They should be x and y values for your points. Unless they say, like, where does it have, what's t when it has horizontal or vertical tangency? Yeah. Yeah, thank you.
Why is it minus 2 root 2?
I know I changed it, it's just frozen. Okay. All good? If you want, for these, if you don't have a calculator, I would just write it as one giant ordered pair and just take 3 halves and do like 3 halves squared plus 3 halves on a free response so that you don't mess up in your algebra. Save yourself some time. Oh, negative 1/2 squared is, oh yeah. See, I shouldn't have simplified. Case in point. I know, I'm fixing it. Hold on 1 second. Wait 1 second. Okay. Case in point. Should have just plugged it in. I should have just written it like this. 3 halves squared plus 3 halves. Comma. And then the other one, you know.
Oh, like
would have been a lot easier. And then you're done, and then you don't have to simplify. And a reader can easily look at that and be like, oh, he just plugged it in. That's good. Or she just plugged it in. I don't think they know your gender. Maybe by your handwriting. Although some people are very... Sometimes I think boys' handwriting is girls' handwriting, and then girls' handwriting is boys'. But most of the time I can tell. Okay. Last part is set up an integral expression for the arc length of the curve. Now, that's interesting because if you have a parametric, let's think about what arc length is. So if I calculate the length of this arc, what is it also equal to? The what? Somebody's saying it. So pretend this is a particle moving along the path. If I calculate the length of this arc, what other value do you think it's giving me? The what? No, it's not giving me the time. The t is... If I know the length of this path, and it's a particle moving, no. Somebody's saying it, but I can't hear. Distance. Yeah, right? Because if I calculate the arc length of this particle movement, I'll know the distance the particle has traveled, yes? Yeah. So just remember, if they ever ask you to calculate distance on a parametric, it's the same thing as arc length. Distance traveled. So that's it's the exact same thing as arc length. Okay, now, what were the arc length equations you remembered from back in the day? You're too fast for me. I'm still just writing arc length. Integral a to b of square root dy dx, right? Squared and then dx. But you can also do the 1 plus, which you almost never see, but 1 plus dx dy squared dx, right? Well, actually, arc length for parametrics is a lot easier. This is the same as integral a to b. You know how we moved the dx over when we calculated this one? Well, we don't have to for parametrics. We can just make it integral a to b of dx dt squared plus dy dt squared, and then it's with respect to t. So it's actually a lot easier for parametrics arc length than non-parametric arc length. Okay? Because you can calculate the x component and the y component separately and just add them together. So it's basically like very similar to distance formula, right? Okay, so do not evaluate, just set up an integral. And most of the time they'll just ask you to set up and not evaluate, so unless you have a calculator, then they'll ask you to evaluate. So we're going from 0 to 1, square root, and it's dx dt squared. So this is, I don't know why I gave myself so much space, 2t squared plus, and then dy dt, 12t squared squared dt. That's it. Not too bad, right? Okay. Need a break?
Yes.
Okay, let's take a 3-minute break. So we have a few things for parametrics and vectors, they usually go hand in, like together, and sometimes your parametrics will be defined as like x of t and y of t, right? And you already know that dy dx is going to be your slope of your tangent line, right, of a parametric. But usually if we're talking about velocity, we'll keep the two components separate. And so you'll do x prime of t comma y prime of t if you want the velocity vector. And acceleration will also keep the components separate. Okay. Let's see, what else? D squared y, this is if they ask you that. That's just, they'll just ask you what it is. Or this will give you the concavity. But it will not give you anything about acceleration of the particle. And then we've discovered that distance, right? We'll go down here. Now distance in regular mode is integral of the absolute value of velocity, right? But distance for parametrics is the arc length, right? Integral a to b of square root dx dt squared plus dy dt squared dt. And then, since we have an x component and a y component for parametrics, then our speed is not going to be, I can't just calculate absolute value of like this velocity vector for speed, right? So speed is going to be the magnitude of this vector. Do you know how to find magnitude of a vector? It's just square root, yeah, x prime of t squared plus y prime of t squared. So I just want the magnitude of the velocity vector. So this is magnitude of velocity. You should know this, guys. If you're in physics, you should know this. And so sometimes I remember, you know, in regular one-dimensional calculus that we were doing, that remember when speed is just absolute value of velocity, right? And then if I wanted distance in one directional motion, then it was just the integral of speed, right? Absolute value of velocity, or the integral of speed. So it's the same thing here. For parametrics, the distance is the integral of your speed, but your speed is the magnitude of the velocity vector. Okay. So these are the few things that you need to know for your parametrics. And then position, you'll calculate two separately, but we'll work on those when we do these problems. All right, so if I just want the velocity vector when t equals 1, then I just got to take x prime of t and y prime of t. So the derivative of t cubed plus 4t squared is 3t squared plus 8t, and 4t cubed minus 3t squared, right? And then our velocity vector when t equals 1 is going to be 11, comma 1, right? Find the acceleration vector when t equals 2. So you just take the second derivative of the original, or the first derivative of the velocity vector. 6t plus 8. And this is 12t squared minus 6t. 12 plus 8 is 20, comma. Okay. Now, example 2 asks you to find the magnitude of the velocity vector given those two parametric equations. What is it asking if you want the magnitude of the velocity vector? What is your speed, right? So if it asks you for speed or magnitude of the velocity vector, then that's the same thing. Okay, I want you to do example 2 for me, because we already went over what the magnitude of the velocity vector is. I'll go back to that page so you know. Okay. What'd you get? Is your answer? Sounds good to me. Okay. Example 3 asks you to write an expression that represents the distance traveled by the particle between the two x-intercepts. So distance traveled for a parametric will be what? Arc length. So integral 0 to 2 pi square root of dx dt squared plus dy dt squared dt. And the derivative of x is 4 sine t, yeah. And the derivative of y is negative 2 cosine t. Okay. Nice. Oh, wait, not 0 to 2 pi, sorry guys. We have to now calculate, thanks Jordan, our two x-intercepts. How do we calculate x-intercepts? Good. You guys are on a roll. So 0 equals 1 minus 2 sine t. 1/2 equals sine t. T equals pi over 6 and 5 pi over 6. Now we've got our bounds and we're done. Okay? All right. Example 4, a particle moves in the xy plane. Here's x of t and y of t. For what values of t is the particle at rest? So, what does that mean? velocity equals 0. So since I have a velocity vector of, what is this, 6t squared minus 30t plus 36, and 3t squared minus 6t, I can't just set velocity equal to 0 here, and I don't just want one of them to equal 0. At rest means both dx dt and dy dt have to equal 0. Because if only one of them equals 0, then it means it's still moving in the other direction. So for example, if dx dt was equal to 0, but dy dt was not, then that means it's still moving up or down. It's just not moving left or right anymore. Similarly, if dy dt equaled 0 and dx dt did not, then it means it's still moving left or right, but it's not moving up or down, right? So you want both of them to equal 0. So set both of them equal to 0. And find where both of them equal 0. I'll give you a minute. One more problem together, and then the last problem is on your own, and then we're done. Okay, this one should have been, did you get it equals 2?
Yeah.
Okay, so at 3 it has only vertical movement, and at 0 it only has horizontal movement at those two locations. Okay, example 5 is, now they give you a velocity vector and they want your position of the particle at t equals 1, and they give you that the position of the vector at t equals 0 is 7, negative 4. So you want to use fundamental theorem of calculus to calculate where you are at t equals 1. So we're going to find x of 1. Oops. X of 1 is going to equal, where do I know I am initially? 7 for x, right? So it'll be 7 plus the integral of the x component, 3t squared minus 4t dt. And I'm going to integrate from my value I know, 0. So at 7, I'm at 0, right? At t equals 0. And then the 1 is going to be where I want to be at the end. So that's going to be 1. Okay. So that's x of 1. Let's go ahead and finish it. So it's just 7 plus, and then this will be t cubed minus 2t squared from 0 to 1. And if I plug 1 and 0 in, it'd be 7 plus 1 minus 1, so 6. And then I find y of 1. What's y of 1 going to equal? Negative 4 plus integral 0 to, I want 1 of dt. And then we finish. At cubed is 2t to the 4th plus 5t from 0 to 1. Negative 4 plus 2 plus 5, 7, 3. So our position of our particle at t equals 1 is 6, 3. Okay? All good? All right. Your job is to finish number 6. You can use a calculator. And then after you finish 6, you're done for today.